for the people in the back. Can you hear me? There are some seats up front here if you want to be comfortable. Good afternoon. Thanks to DerbyCon for having me, and thanks to all of you for coming. This talk is Intrusion Hunting for the Masses, a practical guide. Can you guys hear me okay in the back? By the way, there are a lot of slides in this presentation. I might go fast for you to write down command syntax and notes. I have already posted the slides out on SlideShare if you want to follow along. I tweeted the URL out at Sharpe Security on Twitter. The Twitter address account is up on the screen there. First, a disclaimer. Opinions expressed in this presentation are my own. I'm speaking for myself, not for GE, nor anyone, nor anything else. I am David Sharpe. I started off in IT and systems programming about 20 years ago, and I've worked in a variety of roles over the years. I've spent the last 10 years focused more on IT security. For the past 4 years, I have worked for GE CERT. Why am I here? I believe that we are finding fewer and fewer high-end APT intrusions across the board. I believe this general downward trend in detection is spread across all industries and is worldwide. I am not saying that there are fewer high-end intrusions. I am saying that we seem to be finding a much smaller percentage of them compared to just a few years ago. Why the drop-off? Have attackers lost interest? In my experience, that's a no. Are we generally all better defended, or are systems becoming impossible to breach? I think that is a no. Harder to breach, yes. Impossible, no. Have we become less effective at finding intrusions? Maybe. For the sake of discussion, let's pretend that there are 5 skill levels of targeted attackers, assigned school letter grades ranging from A through F. Hacking RSA to abuse tokens to enter a target, A game. Stuxnet, A game. Using exploitation, C2, lateral movement, and exfil techniques from 10 years ago, D game. Spearphishing the same way that you have for the past 5 years, F game. Frankly, we all struggle with finding PhD-level attackers bringing their A game. Many of us struggle with attackers in the B to C game level. Many have success finding attackers using D or F game tactics, but is that good enough? I think there has been a general upward migration on the attacker side to the A to C game level, and that has at least partially blinded us. Maybe we have hunted most of the D and F game activity to extinction over the past few years, and haven't kept up with the A to C level offensive side operators yet. The purpose of this talk is to share several effective techniques to find intrusions at all those levels, from sophisticated A through to humble F. So, what's working for finding intrusions these days? That, in my view, breaks down into 2 broad buckets of activity. 1, detecting list of known bad things, indicators, through mostly automated network or host detection systems. That approach is still effective and essential, but isn't what we are covering here today. Another approach is by hunting or manually looking for signs of possible badness across broad data sets. This will be the focus of this talk. Now, manual hunting can and should, where possible, lead to new forms of automated detection. So what about data science? Where does that fit in? Data science is great for a broad spectrum of problem domains. Data science techniques can certainly help inform better detection and hunting practices. In my opinion, the element of time is, in many cases, the most sophisticated data science model element that pays off for much of a search problem set. Not high-end math, not complex statistical methods. Data stacking, a term I first learned from a Mandiant presentation, is another key to success with intrusion hunting. Data stacking basically refers to ways to massage a data set to get the abnormal and interesting things to bubble out of all the normal data. The concept of data stacking will make intuitive sense as we work through the practical examples in this talk. But we are aiming for simple, but effective. Know thy data. Know what data is available on the systems you are collecting from, or what you can derive from what is present or happening on that system. Know what each element or field in the data truly means. Know what badness looks like, and check for signs of that in your data set. If you are wondering what the blue arrow is all about, I use a blue arrow theme in these slides. The way I see things, we all get arrows fired at us regularly by attackers. This talk's purpose is to give you some arrows for your own quiver to fire back, to help better defend yourselves. We will cover 12 practical examples of hunting in this talk. These 12 ideas were purposefully selected to maximize your chances of finding intrusions for all intruder skill levels, A through F, so that you can help reduce damage to your organizations and customers, raise your adversary's cost of operating, and generally speaking, better protect your grid. Let's get started. First, Shimcache and Amcache. If you only act on one thing from this talk, this is it. What is Shimcache and why is it valuable? Basically, Shimcache is bookkeeping data that Windows automatically maintains to support application compatibility. Shimcache is used on XP through Windows 7 on the client side, and from 2003 Server through Windows Server 2008 on the server side. As a side effect, Shimcache gives us a record of what processes have been run on Windows systems for a time span that could potentially span back months or years, depending on the age of the system and how it's been used. If an intrusion happened 2 days ago, 2 months ago, or 2 years ago, this might be your best shot at seeing that. A convenient and easy one-stop shop to see much of what has been ran on the system over an extended period of time. Many intruders of all skill levels, including some of the best attack teams in the world, still don't clean up Amcache or Shimcache, despite their being meticulous about cleaning up otherwise. So play that to your advantage. Sound good? How can you get Shimcache data flowing back for analysis? You can either run this Python script directly from Mandiant, the link is on the screen, if you have a suitable Python runtime environment available on all your Windows machines. Or you can make a Windows exe out of the provided Python script using something like py2exe and deploy that out. If you pull the resulting data back to a central system for processing, you're looking at around 100 KB per machine. You should aim to collect and analyze Shimcache or Amcache from all of your Windows endpoints, both client and server. But servers are the sweet spot. Why? Servers, in my experience, remain the #1 initial entry point for breaches, especially internet-facing servers or other servers and DMZs. Windows clients are also important due to the prevalence of targeted watering hole attacks in recent years, and to a lesser extent, targeted spear phishing. On modern Windows OS versions, Shimcache can be anywhere from a few hundred entries long on a brand new or lightly used system to 1,024 entries on a typical production machine. Shimcache records look like what's on screen. Shimcache records break down as follows. The first field is the last modified timestamp. This is not when the process last ran. It is the last modified timestamp from the file's MFT entry. For newly dropped malware that has not been time-stopped, this field is useful. If it is time-stopped, then at least you know something ran, maybe just not exactly when. Next, the last update field was used only on Windows XP. That was more useful for telling when something last ran. That field isn't set on modern Windows versions. Next, the full path field shows the location of the binary on the file system, so this is definitely a good one for our purposes. The file size field is only set on XP and Server 2003, not anything newer. And the last field is the execution flag. That is a binary field set to either true or false. I haven't found this field useful for hunting, so leave this one alone for now. Consider an example. Here some NTFS entries are time-stopped. These July 2010 dates made no sense given the age of the system and stood out in the data set when sorted by timestamp. Another thing that stood out as suspect were the file paths. Does anything normally run out of C:\Windows fonts? Looking across your entire Shimcache and Amcache data set, you will see the answer is no. The last few commands by themselves could be harmless normal IT or user activity, but in this context also could be scanning or recon since they are grouped together so closely in time. For your reference later, here are several links to more information about Shimcache. Now let's break down Amcache, Shimcache's replacement. Shimcache was replaced by Amcache starting with Windows Server 2012 forward and Windows 8 forward. Amcache is still in use with Windows 10 and Server 2016. Amcache serves the same purpose as Shimcache, but has several more useful fields for hunting. How do you get Amcache data flowing? The source file, windir appcompat programs amcache.hve, is locked on running machines. This registry hive file is small, so one option is an in-use copy of the Amcache file back for offline processing. Then you can run the original author's Python script directly. By the way, I believe the gentleman who developed this script spoke here at DerbyCon this year. I'm not sure if he got as much credit as he deserved for solving this problem for us all. This is a big deal. If you are watching, many thanks to you, sir. With Amcache, you have more useful fields to stack and mine. A breakdown of the available Amcache fields is on screen. There are more fields in Amcache for the attacker to accidentally signal their existence. Some of these fields get set by their compiler or linker and may not be simple to fake, or may be easy to forget about. There are more fields to leave blank when they should be filled out. A lot of ways to make mistakes and give away an intruder's presence. Note the SHA-1 hash field. That is useful to help filter out legitimate binaries from the data set. Now, what should you look for in the Shimcache and Amcache data? Stack this data thoroughly and see what bubbles out. Remember what I said earlier about attackers neglecting to clean this data up. In general, you're looking for any tools that support any of the key actions commonly taken across intrusions: reconnaissance, privilege escalation, credential dumping, lateral movement, data collection, archiving, and exfiltration. At a minimum, check for signs of credential dumpers, sequences of recon activity, net commands, pings, use of scan tools clustered together in time. Look for archivers being ran. RAR is still the big one, and consider 7-zip now too. Look for EXEs running out of abnormal locations on disk. Look for things being ran with short file names like 1.exe or w32.exe. Here is an excerpt from Amcache from a breached machine, found using the Amcache tool's timeline feature. Amcache has a -t argument that you can use to generate a timeline. I had to edit out a lot of fields out of the Shimcache output to fit it in the slide so that you can see an example of what malicious activity might look like in timeline form. There are normally no EXEs present or ran out of the top of C:/users. There is normally not a file named abscan.exe in C:/Windows System 32 either, so that is why these records bubbled out of the data set. I strongly believe a high percentage of you will find an intrusion soon using Shimcache and Amcache only. Here are some links for additional information about Amcache for your reference later. Next, the second highly effective arrow for your quiver. This might sound counterintuitive to some, but antivirus logs are one of the most productive places to hunt for signs of intrusions might be in progress. In my experience, just under 20% of all targeted intrusions involving Windows systems have AV fire somewhere along the timeline. You are missing an opportunity if you don't mine your AV logs. That 20% figure, coupled with the fact that this type of hunting is fairly easy to do, is another one of the reasons I can confidently say that many of you will find intrusions when you go back home. If an intrusion attempt has progressed far enough along to where an AV product triggers, then that is helpful. At best, you have a blocked intrusion, but still there might be an exploitable hole there that needs to be addressed. Worst case is the intrusion is pretty far along, and AV happened to pick up just one tool in a long series of events. Trust me, mine this data, especially server AV logs, and especially for internet-facing assets. What should you look for? Examples include web shells. Look for any web shell street names and watch the file extensions. Look for AV detections where the file is under web root, under C:/Windows, anywhere underneath C:/Windows. Look for detection of any kind of backdoors or intruder tools identified by your intelligence sources and experience. Look for any known bad AV street names, especially for all malware types that we just discussed. Supplement that with custom HIPS detection, with HIPS rules looking for how these targeted malware samples and tools work. If your AV product supports this in some way, even if informational logging only, look for packed executables present on servers. To help illustrate the concept, let's break down credential dumpers a little bit further. The 5 credential dumping tools I most commonly see in targeted intrusions are WCE, PWDump, GSecDump, FGDump, and Mimikatz, in that order. I list some other, less commonly encountered dumpers on screen. Find your AV vendor street names for all versions of all of these dumpers and always look for them in your AV logs. Also, if you have HIPS deployed, what HIPS rules fire when these tools are ran? Hunt for those HIPS logs too, alongside the AV street names. Next arrow. What are you doing to find rogue network listeners across your endpoints, especially servers on the network edges? You can use regular Netstat or a number of tools. More output fields are better. Just run netstat-nabo, pull the data back, and mine it. Let's look at some possible benefits. Netstat-nabo can tell you a lot. In this example, data stacking shows more than one process name and more than one path down to the same TCP port, port 1433 for Microsoft SQL Server on a single system. That is supposed to be impossible. In this case, intruder activity was being interleaved with legitimate SQL Server traffic. Not good. Consider these. Try stacking the Netstat output for all internet accessible servers by listening port and see how many ports show up just once across the entire dataset. Stack output for all internet accessible servers by full path to the listening process's binary and see how many paths show up just once. Preserve all Netstat output as a baseline and track all new listeners that appear over time, especially across your internet-facing systems, so that you can see what changes over time. A caveat. These are just snapshots, not real-time monitoring. So you will likely miss non-persistent listeners, for example, where a new listener spins up temporarily based on only a timer or as a result of port knocking. Next, user agent strings and HTTP traffic can be good for hunting. Be aware that this data set is huge. For stacking, the number of unique user agent strings across a typical production environment can be surprisingly large as well. So, to get the most data out of the captured user agent strings, you have to filter out a lot to get to the actionable ones. Consider stacking the data by user agent string length rather than content, focusing on both the shortest strings and the longest strings of the data set. Also analyze the counts of tokens or the word count in the strings, focusing on the lowest token counts. And lastly, of course, bump the entire data set against list of known bad user agent strings. And please bear in mind that HTTPS blinds you to user agent strings unless you terminate that traffic and log it for analysis. A couple examples. Here, first we have an example of what I mean by a highly unique, low token count user agent string. See the HTTP browser /1.0 user agent string there? It is only one token and is highly unique in production traffic. If you see that HTTP browser string on your network, that is always APT and is always bad. Next, we have a user agent string that has a normal token count and a normal overall length, but should never actually happen in production. So it would show up when stacking. This string, Mozilla 4.0 compatible MSIE 6.1 Windows NT, refers to a non-existent Internet Explorer version 6.1. This particular user agent is only found in certain Metasploit traffic. In my experience, I have never seen an attacker use Metasploit for C2. I have only caught pen testers and red teamers using Metasploit for command and control. Next, Windows services are still commonly encountered in targeted intrusions and have been for years. In large production environments, you will likely find mining your services data productive. Let's explore a few ideas around that. There are a number of tools to dump list of installed services. Most of these tools have similar output and show almost everything you want to analyze for an installed service. Here we show output from Microsoft SysInternal's PS Service tool. Let's see what fields look useful for stacking and analysis. You want to look for rare, unusual, or typoed service registry names or display names. Those are the top two fields in the example shown. A commonly overlooked field when searching for malicious services is the service description. Some malware tries to hide in a crowd of similar-looking services by registry name, display name, and file name, but either typos the description field or leaves it blank altogether, when the service that it is trying to mimic normally has that field filled out. The binary path name field is a good choice for hunting. You want to look for things running out of unusual file system locations, for example, highly unique paths or file names, or anything running out of temp. The example on screen shows one form of what is known as service hijacking. In this case, the service was something that was already present on the machine, but got its configuration changed to point to another malicious executable on disk. For years, attackers have been reporting existing legitimate service configurations to a rogue binary on disk, hoping to escape notice. For legitimate system services, this type of problem shows up when stacking by the right fields. All of your healthy services will point to the right binary path name, or service DLO will point to something legitimate. If you have 10,000 services with the same name and display name, pointing to mostly the same file path and file name, and then just one pointing to something different, that should stand out. Now, over the years, Microsoft has regularly changed the names of legitimate files on disk between OS versions and service pack levels. Despite that fact, one-off malicious service configurations like this will show up when stacking. Hopefully now, with Microsoft releasing fewer service packs and major OS versions over time, this will be less of a problem for us from a data stacking and hunting perspective. Most service analysis tools, including Microsoft's PS Service tool, don't report on one key field, and that is the service DLL value from the registry. The service DLL value for a service indicates what binary gets loaded when a service is configured to live inside of a shared service host container. I am not aware of a free and publicly available tool that can report the service DLL information. As a workaround, we can use Microsoft's listDLLs tool instead. The first command on screen lists all DLLs loaded inside of any service host.exe process. The second command shown lists only unsigned DLLs loaded inside of service host containers. That helps reduce the amount of data to analyze, but remember, some malware is digitally signed. Recall a bit earlier when we covered hunting for situations where legitimate service configurations in the Windows registry were altered to point to the wrong file on disk. This listDLLs approach can help you find the flip side of the hijack service coin, situations where the service configuration in the registry is perfectly fine, but the file on disk has changed. Here we are playing off listDLLs-U to find unsigned drivers loaded across all service host containers. The example on screen is showing where the legitimate Windows error reporting service still has its correct configuration, but its normal signed Microsoft DLL isn't the thing being loaded. The file name is correct, but the file isn't signed, and it should be, so that will require investigation. When you first start mining services data across a mature population of Windows machines, including servers, ones that have been around for years, you might see things like these unique service registry names and display names bubble out of your data stacking. Service names using only GUIDs are easy to spot by searching for the curly brace characters. Garbage service names are often all lowercase characters for some reason. The command on screen can help you spot these across your data set. In my experience, most of these are commodity malware, even when found on servers, and are left over from days when worms were more prevalent. But you have to investigate each to be sure. Next arrow. Similar to services, Windows drivers continue to be a commonly encountered component in targeted intrusions. We break drivers out here to highlight a couple additional things to look for. The commands on screen are an effective way to dump the driver list, with the best fields for hunting included. To dump all driver info, you can use Microsoft's driver query tool with the options shown in the first command. To dump the signed driver information, you can use driver query as shown in the second command. Here is some sample driver query output from a Windows 10 system. There are a number of useful fields here in CSV form that we will cover in a moment. What are some productive things to look for in the device driver's data set? First, the link date field shows when each reported driver was compiled and linked. If that field has been zeroed out or contains an impossible or garbage timestamp, that's interesting. Intruders that timestamp their binaries in the NTFS MFT entries on the file system often do not touch the timestamp that shows up in this link date field. That lives inside the file itself. So if you find a driver with file system timestamps that are months or years older than the file's link date, that could be interesting as well. Next, always examine the path to the binary image of a driver on disk, looking for drivers loading from unusual locations on the file system, for example, any temp location. Does the driver file name itself have unusual characteristics, like the name is all numbers or hex digits? Look for rare and wrong-sounding driver descriptions like the one on screen. Monitoring of hardwares and automatically updates the device drivers. It's gibberish. Mind the display names, looking for the rarest ones in the data set and typos. You might be surprised at how many unique driver names exist across the population of even just a few thousand Windows servers. Look for missing or unusual digital signatures on the driver binary. Eliminating signed drivers to reduce this data set is useful, but please be careful which certs you trust. Some hostile binaries are signed with stolen certs. Here's an example of a device driver that stands out as unique in the driver data set. From a stacking perspective, it is unusually noisy for 3 reasons. That key IP filter driver name is unique in the data set, as is the key IP traffic filter driver display name. So is the driver file name, key IP FLT DRV.sys. Next arrow. Autoruns data from all Windows machines is a productive place to mine as well. Microsoft sysinternal's Autoruns is the go-to tool here, with its comprehensive coverage of most Autoruns locations, all WMI autostart locations, and much more. Also, check out the new WMI parser tool discussed yesterday here at DerbyCon by the three gentlemen from FireEye. This one is really easy to do. Just collect the data and analyze. It is about 250 to 500 KB per machine. The command on screen will collect everything the Autoruns tool can find. Autoruns covers most known autostart locations, but not all. For example, side-loaded DLLs and DLL search order issues won't turn up. Please be aware that you scoop up a lot of non-targeted commodity malware in this net. Please be aware that the Autoruns tool can now do virus total lookups as it executes, but I wouldn't recommend doing that at scale from your production machines. Do that centrally in a controlled way. Here too, you are looking for things running out of uncommon places, executables at the top of program data, top of the recycle bin, app data, or out of any temp folder location. Reducing the data down to just unsigned entries, meaning entries where the string verified with a capital V isn't present, can help reduce the workload. Look for odd short file names like r.exe or 1.bat. Here we have three examples of malware from Autoruns data. The first popped out of the data set due to the single character exe file name and the uniqueness of the launch starting field. The second and third one shows ways that services and drivers can stick out. In the second example, you've already seen that unique description there before. In the third example, you never see a service named Microsoft Cache Service normally across a population of Windows machines. That entry also sticks out due to its not being digitally signed. Next, Prefetch allows you to get an idea of when certain processes have ran from a different perspective than Shimcache or Amcache. Prefetch is a system performance enhancement present and enabled on Windows client machines from Windows XP forward, including Windows 10. All that we are doing here is taking advantage of another set of data that Windows already maintains. Prefetch is not enabled by default on Windows servers. Prefetch is disabled by default for modern SSD drives, even on client platforms. Up to 128 files can be stored in Prefetch on XP and Windows 7. From Windows 8 forward, that limit increased to 1,024 entries. Prefetch is stored in system root/prefetch. The individual files themselves use a binary format, so you need a tool to parse them. Now, please be selective which tool you use to dump Prefetch data from your systems. Some approaches just look at the NTFS MFT data for each entry in the Prefetch folder. Try to favor tools that do that and have the capability to analyze inside of each Prefetch file. One quick way to tell the difference is if you have a run count field in your Prefetch output. There have been subtle changes in the Prefetch file format between Windows versions over the years, so favor Prefetch dumping tools that keep up with the latest Windows versions. NERSOFT's OnePrefetch tool is the one example that works. An example of its syntax is on screen. That syntax will dump out output in a CSV file. Let's take a quick look at the data available. This is a single Prefetch record as reported by NERSOFT's OnePrefetch View tool, ran from the command line with text-only output, not the CSV format. See that short hash string in red? That is a hash of the file that ran's path on disk. For stacking purposes, be aware that the hash value algorithm changes between some Windows versions. There are three useful timestamps: the created and modified timestamps from the file system, and a timestamp that records when the process last ran. Those are all good for context. The process path is important to help find things running out of odd places. The run counter field can help tell what runs normally from what ran just once. Now, malware can auto-start and have as high of a run count as legitimate software, but intruder actions like running credential dumpers and issuing recon commands might happen only once. What's the most productive way to approach the Prefetch data set? Stack by the various fields we just covered, and consider the timeline. Certain commands in sequence might be a problem. For example, credential dumpers, recon, scan tools, netping ran closely together can be a sign of trouble. Watch for short names in the process exe field, especially if the run count field is 1 or close to 1. Here's an example of an intrusion where we have unusually named Prefetch entries in the data set from a single source machine, clustered closely together in time, within 7 minutes of each other in this case. This was taken from the example that we covered earlier where the w32.exe, w64.exe, and dump pwd binaries lived in c:/users at the top of that folder. As is common across many intrusions from many actors, they have renamed common tools. Because they show up in Prefetch, this is further proof they have executed. Next, error number 9. How do trustworthy and reliable outside services that routinely inspect or crawl your internet-facing assets see you? What do I mean by that? One example, Google, as part of its normal internet-wide crawling activities, sometimes sees signs of malicious content on your internet-facing assets. Anyone can view that data by using Google's safe browsing. In the example on screen, I asked Google Safe Browsing what it thought about the website DerbyCon.com. It came back totally clean. Here's an example of a website that Google didn't consider clean. For sites that you own, if Google knows about a problem and makes that data available to you for free, why not mine that data? In my experience, Google Safe Browsing has a very low false positive rate. Now, when Google does find something wrong with a site, that doesn't mean it is a sign of targeted activity, but I think it is still something we want to know about. Here we show how to manually check all of your websites using Google Safe Browsing. Do this only in compliance with Google's terms of service. The first step is to take your entire domain list and construct the full URLs for wget. Next, we query Google Safe Browsing using wget. This command pauses 10 seconds in between gets to avoid getting your source IP locked out by Google. Don't flood Google with these requests. Spread them out over time. The results will be written to disk, one file per check. If you check 1,000 domains, you get 1,000 disk files with results, one per domain. To find any problems reported back, you can search the files returned using the greps shown on screen. Please use them both to be thorough. Google provides an API for doing this as well. Instructions are at the link on screen. But basically, you apply for a Google API key. That API key allows you to programmatically submit requests to Safe Browsing, including giving you the ability to bundle up to 500 lookups per request. Any sites that Google Safe Browsing thinks have an issue return with the string malware in the response body and HTTP status code 200. Otherwise, you get the string OK and HTTP status code 204. Full details are on the links on screen. Next recommendation. Consider mining your NTFS file system MFT data across all your Windows systems. One thing to look for there are entries that normally have empty extended attribute fields that now do have data in them. Extended attributes in NTFS are a way to store extra information or metadata about a file, information that isn't normally part of the file system's bookkeeping. Most files on an NTFS file system don't have anything in the extended attribute fields. It is normal and acceptable to use extended attributes, if need be, but unfortunately, some high-end malware authors have adopted a technique where they might hide some hostile content in extended attributes as well. How can you find this type of activity? Here's one technique. First, you need to grab the raw MFT from each Windows endpoint. In the example on screen, we use HB Gary's fget tool to do that. The MFT is locked on running Windows systems. Next, chop the raw MFT into usable fields. In this example, we are using analyzemft.py for that. The download link is on screen. This step provided us with a CSV file with the MFT parsed nicely into fields. Locate the EA and EA information field columns in the CSV. Reduce the data to only include rows where either of those fields show as true. Whitelist out what is normal in your environment to further reduce the data and analyze what's left. When you reduce the data this way, it goes from huge to a much smaller percentage. Things like Windows/WinSXS or Windows CSC can normally be whitelisted, as you can see on screen. You will see the patterns of normal across your machine population. Analyze what's left after whitelisting those out. If you do find something require further analysis, you need to extract the contents of what the EA entry points to. Great work has already been done showing ways to do that. On screen are 2 links I recommend for full details. If you need to extract any data or contents from an EA entry, you have to do that on the source machine or from a full disk image taken from the source machine, because the data contents likely won't be in the MFT that you extracted. This isn't always high-end APT malware. It can be things like advanced cybercrime malware, but it is worth mining. Next, how might you know if a high-end adversary shoots a 0-day error at you and it sticks? One that has never been seen before, a true 0-day. This is one tough problem. This is more in the realm of a PhD-level attacker bringing their A-game versus D to F-game activity. Most of us have to depend on catching something later in the kill chain, but we can try to catch the exploit in some cases. EMET log mining might be one possible way forward. What's EMET? EMET stands for Microsoft's Enhanced Mitigation Experience Toolkit, and is a set of mitigations that you can add on to Windows to help protect against a range of exploitation techniques. It is most commonly deployed on Windows client platforms and works for protecting most everything except Java runtimes. EMET works on Windows servers too, from 2003 Server forward. EMET logs go into the Windows application event log. Basically, if EMET sees something is wrong, it takes whatever the prescribed action is and records that in the application event log. Not everything EMET logs is 0-day. You might encounter bugs or misbehaving applications that cause EMET log noise. However, you might be able to find use of 0 days there, looking at what EMET has blocked. If you see where EMET mitigated or killed iExplore.exe or Office or your AV product and your machine is fully patched, that could be a bug or crash that looked like a problem to EMET, or it could be a thwarted exploitation attempt. You should know when this happens. Here is an example from July 2015 where a high-end APT actor was phishing using one of the Adobe Flash Player 0 days leaked from the hacking team dump. If you rolled EMET out with the EAF mitigation enabled, then EMET blocked their exploit code upon execution. The blue text on screen is what EMET logged in this case. EMET detected EAF mitigation and will close the application iExplore.exe. If you didn't find this phish attempt another way, this could have been your only chance to know an attack had been attempted. If you have rolled out EMET across your Windows client and or servers, EMET log mining should be an effective 0-day detection method for you. Next, our 12th arrow. Consider proactively pulling back Windows RAM dumps from select systems and processing them. Maybe it is too much to attempt all of your systems due to the amount of data being collected, being multiple gigabytes per machine. Maybe focus more on pulling RAM dumps back from key systems, internet-facing systems, or ones you're most worried about for one reason or another, for example, interesting machines from new company acquisitions. RAM dumps have many more nooks and crannies in which to look for anomalies and signs of intrusion, but it is a huge amount of data. The good news is that you can script RAM dump analysis to an extent with tools like the Volatility Framework. First step, how do you get RAM dumps? There are a variety of tools available, most work similarly, and many are free. However, almost no Windows RAM dump tools collect everything, for example, video RAM and device memory ranges. Try to select RAM dumping tools that can reliably and safely collect everywhere that malware can hide. George Garner's K&T tools is an option. Hardware dumpers are another option, but those are a bit more costly and intrusive. Next, we will quickly walk through a few volatility commands to give you an idea of what I'm talking about. There are many useful commands in volatility. We just highlight a few of them here due to limited time. First, Volatility's malfind plugin is intended to help identify malicious code injections. It looks for memory pages that are mapped into a process with no associated memory mapped file, and that memory page has to have permission set a certain way to be considered suspicious. Malfind returns a lot of false positives, but it's still useful. Look for MZ headers and fully nulled out hex dumps in the output. Service scan lists Windows services found and has stackable output, like the binary path field. The -v argument on screen gives you the service DLL field, so definitely use -v. Loader modules list DLLs that it finds loaded. Look for when the file path is blank when it should be filled out, and stack the data. For example, see what DLLs show up only once. Look for other anomalies, like things running out of uncommon file system locations. Watch for any fields that are 0 when they should have a value, or are blank, or say unknown in all caps when they should be filled out normally. The first loader modules command on screen helps you filter the return data down. By default, it is a long list. The second command can help you find low-hanging fruit where things are loaded out of unusual places on the file system. PSX view gives you a process listing from the perspective of several different process-related bookkeeping mechanisms within the operating system. If malware tries to hide its presence in one or more of these lists, you want to know about that. The command on screen takes the normal PSX view output and prepends a field to each row of output, showing the counts of how many of those lists each process is in. It sorts the output so that the weirdest processes pop out at the bottom and similar processes get grouped together for analysis. The timers command can enumerate certain types of Windows internal timers. Look for the uppercase string unknown, and the output is productive as a first step in triaging the timers command output. The callbacks command lists a wide range of OS and application callback mechanisms that it finds. This returns a large list on most systems. If you see the word unknown in all uppercase for any callback, that is normally something you need to look into. Otherwise, you need to search the callbacks for known bad indicators. Also, a lot of high-end APT malware uses callbacks, so when you analyze malware samples, try to collect the module name, the callback types, and any names used, and compare that list to the callbacks that you dump out of collected RAM dumps. Next, what are you doing to find BIOS or firmware implants across your server and client hardware population? This is another tough problem. One approach might be to use MITRE's Copernicus tool. The approach there is to dump out as much system board BIOS and firmware as you can, and mine and monitor the files and data that you collect. Whether we are talking about system board BIOS or firmware in hard drives, or supporting network or graphics hardware, we are currently at a pretty lopsided disadvantage as responders and defenders. Implants in BIOS and firmware typically leave little to no detectable trace. But we need to do the best the current state of the art allows us to do, right? For example, the Art of Memory Forensics book, the citation and authors are listed on screen, has some interesting suggestions for detecting certain types of BIOS and firmware implants. One suggestion is to check the real mode interrupt vector table for signs of tampering. Another is to check the uppermost addresses in real mode memory to see for any traces of an implant. What's on screen was taken from a dump of physical RAM from a 32-bit Windows 7 machine. Using the same technique on 64-bit Windows 7 works fine as well. The real mode interrupt vector table normally starts at offset 0 in physical memory and runs for 1,024 bytes. You can tell if you're on the right track if you see repeating 4-byte sequences there. Those are pointers to interrupt handlers. The first 4 bytes store the handler for interrupt 0, the next 4 bytes are for interrupt 1, and so forth. This shows command syntax to generate a more structured dump of that same real mode interrupt vector table in a format easier for data stacking and analysis. That command will list all 256 possible interrupts in the table with the address of the associated interrupt handler. The addresses starting with F000 point inside standard BIOS. The C000 is normally video BIOS. You're looking for what isn't normal here, what could have been tampered with or hooked by an implant. The second suggestion from the authors of the volatility book was to inspect the uppermost addresses in real mode memory for any traces of an implant. Here I suggest you deviate a bit. If you have indicators, strings and byte sequences that can detect a particular BIOS or firmware implant, then I believe that it's better to scan your entire RAM dump, including what you captured from real mode memory. That sounds more thorough to me in case any indicators leak outside of real mode address space due to how the implant works. Also, it is better to search the entire physical dump as a binary blob, in addition to the structured searches using tools like volatility that may be checking only process address space or kernel space, depending on the circumstances. So, do your structured searches in volatility with its Yara support is effective for these purposes, as the examples on screen demonstrate. But also search the whole RAM dump file for the same indicators like an ordinary binary file to make sure that you cover the entire physical address space. A third suggestion from the volatility book is for hunting for implants is to see if something called the IO APIC indirect access registers have been tampered with to reroute interrupts. APICs and IO APICs are pieces of hardware used to support processing of interrupts on multiprocessor systems. I don't have a scripted volatility command ready for this one yet, so I'll instead show you the manual steps to get this data using the Windows kernel debugger. This output on screen is from a 32-bit Windows 10 machine. The process goes like this. Either you have to convert your RAM dump to Windows crash dump format, and volatility can do that, or collect it in Windows crash dump format to begin with, as many memory dumping tools can do. Then open that crash dump file in the debugger. In this case, I'm using the command line KD kernel debugger, but WinDBG works just as well. I issued a .log open command to save the contents of the session to preserve the IO APIC command output. And then you type bang IO APIC, IO APIC, to dump the IO APIC data out for later comparison and analysis. The idea being to look for deviations from normal in this data set. For example, where an implant might be reporting one of these addresses for its own purposes. This might be good for a volatility plugin later. Lastly, a few closing thoughts. After working on any new intrusion, in post-mortem, think carefully about exactly what could have alerted you to that intrusion earlier, as well as along every step of the intruder's path. Add to your hunting process as required. Go back through your entire case history, all historic intrusions, and do the same. What could have found that intrusion earlier or more reliably? When you read about intrusions affecting others in the news, mentally do the same. Could your organization have found that intrusion earlier on your own? Be consistent. Convert as much of your manual hunting processes to automated detection as you can. Managers, please fund your hunt functions and don't back off just because the volume of detected intrusions found might be low for extended periods of time. It's tougher out there now. And finally, stay vigilant and keep elevating, raising the quality of your detection and response processes always. I'd like to thank you for your time. I'd like to now open up for any questions, but this is the last talk of the day, and I think they're converting the room to prepare for the full closing ceremony. So if you'd like, I'll be hanging around out here for questions. Thank you very much.